Hi friends, welcome back to my YouTube channel. So today I'm going to discuss about computer communication. So this is from EC 407 computer communication for KTU syllabus, and I'm discussing about error control, and this is from ignore this part 3 and this is not part 3. I think this is a part 5 of that topic from error control. So we are now going to discuss about checksum. So checksum is one of the activities. So it's used for error detection method, and we have discussed a lot of detection method previous slides. So the last error detection method we discussed here is called checksum. So this is the last one from that, and the checksum is used in the internet by several protocol, although not at the data link layer. However, we briefly discuss it here to complete our discussion on error checking. The linear and cyclic codes, the checksum is based on the concept of redundancy. Like linear and redundancy checks or cyclic codes, the checksum is based on concept of redundancy. So several protocols still use the checksum for error detection, although the tendency is to replace it with CRC. So it's has the tendency to replace it with CRC, cyclic redundancy check. This means that the CRC is also used in layers other than the data link layer. So idea of checksum is, the concept of checksum is not difficult. So we can discuss or describe that with an example. So suppose our data is a list of 5 4-bit numbers that we want to send to a destination. So we have 5 4-bit numbers. We have a list of 5 4-bit numbers. In addition to sending these numbers, we send the sum of these numbers. Example, if the set of numbers are 7, 11, 12, 0 and 6, we send 7, 11, 12, 0, 6 and 36, where 36 is the sum of the original 5 numbers. So the receiver adds the 5 numbers and compare the result with the sum. If the two are the same, the receiver assumes no error, accept the 5 numbers and discard the sum. So this is happening in the checksum. So we have a 5 4-bit numbers. So like example, so we have a 5 number, we are adding that and we are sending it to receiver, and receiver checks whether receiver adds the first 5 numbers and check whether it is equal to the sum of the numbers, that is the sixth number, and if it is same, it will accept and discard the sum, and if it is not, it will send a failure or it will discard the input. So this is happening in checksum. Another example 2, we can make the job of the receiver easier if we send the negative complement of the sum called the checksum. So we can make the job of the receiver easier. We send the negative. Negative means complement of the sum called the checksum. In case we send 7, 11, 12, 0, 6 and minus 36, the receiver can add all the numbers received including the checksum. If the result is 0, it assumes no error, otherwise there is an error. So one thing we send, if the first example is like we send 5 numbers and with the sum of those 5 numbers, and the receiver checks the sum of the numbers equal to the addition of that 5 numbers, and if it is equal, it will accept. If it is not equal, then it will not accept it. And in this case, we are sending the negative or the complement of the sum. That means if the 36th number sum of the 5 numbers, then it will send minus 36. So what will the receiver do? Receiver will sum all the numbers, and if the sum is 0, that means it will cancel out that summation. The previous method we are adding those numbers, here we are cancelling out. So one is negative, one is positive. So we will get a 0. If the result is 0, no error, and otherwise there is an error. So it will not be accepted at that time. If it is 0, then it will be accepted. So we can more discuss about the ones complement. So we have, I think this is a basic concept of binaries and ones complement. So the previous example has one major drawback. All our data can be written as a 4-bit word, they are less than 15 except for the checksum. So one solution is to use ones complement arithmetic. So in the arithmetic, we can represent unsigned numbers between 0 to 2 raised to n minus 1 using only n bits. So if the number of numbers has more than n bits, the extra leftmost bits needs to be added to the n rightmost bit. That means wrapping. So if the number has more n bits, then we need to add extra left bits to the added and n rightmost bits wrapping. So in ones complement arithmetic, a negative number can be represented by inverting all the bits. That means 0 to 1 and 1 to 0. So this is the same as subtracting the number from 2 raised to n minus 1. So ones complement is that we are changing the ones into 0 and zeros into 1. So how we can represent the number 21 in ones complement arithmetic using only 4 bits. So the solution is the number 21 in binary is 1 0 1 0 1. So it needs 5 bits. So we can wrap the leftmost bit and add into 4 rightmost bits. So we have 0 1 0 1 plus 1. So it will get 0 1 1 0 or 6. So we can wrap it like this. So the 21 can be represented in 4 bit 0 1 1 0. So we are adding the leftmost bit with the rightmost 4 bits. So example 4, like how we can represent the number minus 6 in ones complement arithmetic using only 4 bits. So in the ones complement arithmetic, the negative or complement of a number is found all by inverting all bits. So positive 6 is 0 1 1 0, negative 6 is 1 0 0 1. If we consider only unsigned numbers, this is 0. See, this is 9. So if we consider the unsigned number, this is 9. So in other words, the complement of 6 is 9. Another way to find the complement of a number in ones complement arithmetic is to subtract the number from 2 raised to n minus 1. So 16 minus 1 in this case. So for example 5, let us read exercise 2 using ones complement arithmetic, and figure shows a process at the sender and the receiver. The sender initializes the checksums to 0 and adds all the data item, and the checksum is considered as the data at the item in the shown color. The result is 36 if it added all the numbers. However, 36 cannot be expressed in 4 bits. The extra 2 bits are wrapped and added with the sum to create the wrapped sum value 6. In figure, we have shown that the details of binary. The sum is then complemented, resulting in the checksum value 9. So 15 minus 6 equal to 9. And the sender now sends 6 data items to this receiver, including the checksum 9, and the receiver follows the same procedure as the sender. It adds all the data item including the checksum, and the result is 45. The checksum, the sum is wrapped and it becomes 15, and the wrapped sum is complemented and it becomes 0. Since the value of the checksum is 0, it means the data is not corrupted, and receiver drops the checksum and keeps the other data item. If the checksum is not 0, the entire packet is dropped. So if you see in the figure, you can see there is a sender side and receiver side, and the numbers are 7 11 12 0 6 and 0. So the sum of these numbers is 36, and we will get a wrapped sum. So the 36 will need 6 bits are there, so we need to change the 6 bit into 4 bit data. So after changing the 4 bit, we will get the wrapped sum as 6, and after complementing this one, the checksum what it is mean by checksum? It is ones complement of that sum. So we are inverting all the ones into zeros and zeros into 1, we will get the checksum as 9. So this is sent to the This is sent to the receiver side. So we will send a packet of data 7, 11, 12, 0, 6 and 9. 9 is a checksum. So details of wrapping and complement is given here. So you can check that 1, 0 is added with the 0, 1, 0, 0 and we will get 6 and then it is complemented. And the receiver side, what it will do, so it will do like it will get all the numbers and it will add those all the numbers, add all the input numbers and it will get 15 and it will wrap the sum. So that means 1 0 1 1 0 1 0 1 1 0 with the 1 0 and it will get 1 1 1 and it is 15 and once complement it will do the reverse process so that all zeros into ones or ones into zeros and we will get 0. So the checksum is 0 here, so the result is 0 and that's why we are saying that there is no correction in the input data, so it will accept the data frame. So this is happening in checksum using the ones complement method. So internet checksum. So traditionally the internet has been using 16-bit checksum. So the sender side and receiver side. So sender side, the message is divided into 16-bit. The value of the checksum word is set to 0 and all the words including the checksum are added using ones complement addition. The sum is complemented and it becomes the checksum. Checksum is sent with the data. Receiver side, the message including checksum is divided into 16-bit of words. All words are added using ones complement addition and the sum of the complemented and become the new checksum. If the value of checksum is 0, the message is accepted, otherwise it is reduced or rejected. So here you can see an example. For example, the text needs to be divided into 2 bytes. That means 16-bit words. We use ASCII to change the 2 byte to a 2-digit hexadecimal number. For example, F is represented as 046, 0x46 and O is represented as 6F. And figure shows the checksum is calculated at the sender side and receiver side. So figure A, value of partial sum of for first column is 036 and we keep the rightmost bit 6 and insert the leftmost right digit 3 as the carry in the second column. And note that if there is any corruption, the checksum is recalculated by the receiver is not all zeros. So this is a figure for receiver side and sender side. So carries, so there are 5 numbers. So you can check this figure, you will get an idea what I informed before and what I said before. So this is the 8 characters for Ozan. So we are dividing or we are changing that using ASCII and what we are doing, F is meant by 046, so we are 46, so 46 and O is present by 6F. So likewise we are changing this into hexadecimal bits, hexadecimal numbers. So all the Ozan bits are changed into hexadecimal bits and we are adding those, and we are adding with checksum initially it is 0 and we are adding with that one and we are having that carriers with 1 0 1 3 are there and we are adding that. So once adding we are getting the partial sum as 8FC6. So we are getting one carry, one is the carry of after the summation and we will again submit and we will get 8FC7 and then we are changing, we are like complementing that one, we will get FA7038 and this is sent into the receiver side. So here what happens, it will again multiply or add those number, add the checksum with the numbers. So once it is added the checksum with the all the input numbers, it will get partial sum as FFFE and there is a carry of 1, and it is added again and it will get FFFF as the sum and the checksum value is then 000. So we will get a sum of 0. So that means there is no correction in the data and it will be accepted. So the next one is performance of the checksum method. So traditionally checksum uses all the numbers of bits 16 to detect errors in a message of any size, sometimes thousands of bits. However, it is not as strong as the CRC in error checking capability. For example, if the value of one word is incremented and the value of another word is decremented by the same amount, the two errors cannot be detected because the sum and checksum remains the same. Also, if the value of several words are incremented but the total change is multiple of 65535, the sum and the checksum does not change, which means the errors are not detected. Fletcher and Adler have proposed some weighted checksums in which each word is multiplied by the numbers, its weight that is related to its position in the text. This will eliminate the first problem we mentioned. However, the tendency in the internet, particularly in designing new protocol, is to replace the checksum with CRC. So that is all about checksum. So thank you for watching my video. If you have any doubt or any questions regarding this topic, please post the same in the comment box and I will try to answer that question as soon as possible. So thank you for watching my video. Like, share and comment, and see you in the next video with a different topic for the computer communication one. So thank you. See you.